In this video, I'll show my approach how to tackle an object detection task in the important and diverse field of medical imagery. The dataset of the specific project I'll talk about was created by the institutions appears on the slide and hosted at the Kaggle community platform. This dataset involves chest X-ray scans of positive and negative COVID-19 patients, and the goal was to build and train a model that will identify and accurately localize COVID-19 related opacities in the lungs using rectangular bounding boxes. But instead of diving directly to the model chosen architecture and the training algorithm, it would be wise in this case to put some effort in pre-processing. A quick literature reading on the subject of chest X-ray imagery teaches us that the bones, the ribs in the chest X-ray, may significantly decrease the accuracy of detection and localization of the object of interest. So removing the bones from the X-ray image, if possible, is highly recommended as a pre-processing stage. The operation of suppressing the marks of the bone from X-ray image could be seen as a kind of a noise elimination task, and for that we will use a machinery that is called Denoising Autoencoder. Autoencoders in general belongs to the unsupervised side of the table of machine learning, and they can serve as a very effective tool. Their ability to compress the data into high-level representation without the need for manual annotations and label could be valuable and helpful to many supervised tasks. A well-trained convolutional autoencoder in particular will find for us spatial structures and patterns in the data, and this ability could also be harnessed to certain types of denoising tasks. Now, we need to emphasize here that the available bone removal training dataset is not similar and completely disconnected from our target dataset. This bone removal dataset was created by the Japanese Society of Radiological Technology and hosted also by Kaggle. This dissimilarity between the two datasets will require our attention later. I based my convolutional denoising autoencoder for bone removal on the simple yet effective VGG architecture. VGG models have surprisingly good reversibility, which is a very important attribute in pixel-to-pixel models. The encoder part of this bone removal model is similar in essence to any other basic convolutional model. It composed of stacks of convolutional layers to capture the shapes, separated by pooling layers that forces further compression of the spatial information and moving one step forward to a higher level of abstraction. The dimension of the bottleneck in my model are 32 by 32 with 112 channels. After the latest representation come the decoder part of the denoising autoencoder, where the model gradually projects the compressed representation back to the original dimension. Notice that I didn't use here the convolution layers, instead I used upsample operation followed by regular convolution. The advantage in this alternative technique is that it prevents a checkerboard artifact that frequently result from using pure deconvolution operation. Also notice that I do not use here regular max pooling operation in the encoder, nor its mirror standard upsample operation. Instead I use indices skipping max pooling, such as suggested in the Segnet manuscript from 2017. This allowed to upsample the feature to their exact original location as they were before the corresponding max pooling. Now, as I already mentioned, we must bear in mind that the bone removal training dataset is not the one we really care about here. It is just a preprocessing tool for us, and the fact that it is completely different from our target dataset could impose a problem. While the bone removal training dataset composed of high-quality, pretty similar condition images, our target dataset is more of a real-life data. It contains much more diverse qualities, sizes, anterior versus posterior directions, angles of scan, brightness level, and flipping grayscale color maps. So what we need to do is to worsen the bone removal training dataset in a way that it will get some resemblance to the target dataset. We do that by augmentation that includes small 0 to 20% random zoom-outs, minus 10 to plus 10 degrees random rotations, small random shifts, and small random mild blurring. The bones removal model that I built here has 9.5 million trainable parameters, and it was trained in the standard way, but let it follow the gradient on the loss manifold for 12,500 training steps run on a single GPU machine. I used small mini batches of 4 images and used the well-known optimizer algorithm Adam for navigating the neural network on the loss manifold to board a good self-organization of the model parameters. Here you can see some examples for the performance of the trained model. Notice that the presented images here are belonging to the test set of the bone removal dataset, not the target dataset. In each column, the upper image is the original one, after applying to it some random augmentations. The lower image is the ground truth, and the middle image is the prediction of our trained model. And here you can see some examples for the bone removal abilities of the trained model on the target dataset itself. Each upper image is the original one, and the lower image is the prediction of the bone removal model we just trained. The results, although not perfect, are reasonable enough for our current purpose and allow us now to move on to our main goal, building a training and COVID-19 opacities detector on chest X-ray scans. Object detection algorithm could be crudely divided into region proposal versus non-region proposal methods, and also to anchor-based versus anchor-free methods. So, what type of a method should we choose for our main implementation for this specific medical imagery related project? The state of the art in object detection is still, in general, region proposal based methods, such as the well-known faster RCNN algorithm. But the non-region proposal methods, such as the YOLO algorithm, are starting to catch up and close the gap. My personal opinion is that today, keep dividing the object detection task into two-stage process, when both submodels are operating anyway on the same feature map, is cumbersome and no longer justified. It is reasonable to assume that it is only a matter of time until the right technique will be found, and non-region proposal methods will match their performance with the state of the art in the field. The anchor-based versus anchor-free question, however, is a different kind of a story. Although there is something very clumsy and annoying with methods that use predefined anchors, we cannot say that they are not justified. It is not a coincidence that the first version of YOLO algorithm was anchor-free, and then it's only its later versions, the creators, returns to use anchors. The main contribution of predefined anchors comes from the fact that they explicitly enter the requirement for multi-scales and multi-shapes differentiation abilities to the core of the training process, and they do that by incorporating this requirement into the very basic structure of the loss manifold. The second advantage of anchor-based methods lies in the fact that it allows to achieve multi-scale abilities even when using a model that can look at the input only in one fixed scale, or in other words, it has only one fixed receptive field. Predefined anchors also makes it easier for the model to regress the bounding box around the opacity correctly from a pure technical computing power perspective. Despite all this, after consideration, I chose for the current specific project not just to use non-region proposal methods, but also keep it anchor-free. The basic concept behind my implementation lies somewhere in the middle between YOLO version 1 and the more novel FCOS algorithm. One of the reasons I chose not to use anchors and try to directly regress the bounding boxes around the opacities is in that in the 2020 FCOS manuscript, the writers demonstrated that there are indeed ways to direct the process toward multi-scale and multi-shape differentiation abilities other than only using predefined anchors. Another reason for going to the anchor-free direction involves the nature of the specific medical imagery task, which is very different from detecting, for example, very structured real-world objects. As you can see in the ground truth bounding boxes in the image, here we try to detect amorphous opacities. As there aren't really any high-level structure inside the opacities, much of the advantage of the convolutional model are being lost here, and with or without anchor, our model, anyway, will not have the ability to correlate small-size receptive field to larger characteristic shapes. Anyhow, supplying our model with real multi-scale and multi-shape observation abilities are essential here. There are several ways to do that, and one of them is using an inception module. By putting in the same convolutional layer several sizes filters together, this results with a feature map that contains different receptive field channels. It also let the model decide by itself the appropriate combination of receptive fields that are most fit for the task, as the parameters that weights the inception model feature map channels are incorporated into the loss manifold access. Inception models do have some drawbacks. Their reversibility is not so great, meaning that they tend to lose information. So we want to use them with some caution and only when necessary. Because of that, I put in the model's first two blocks, which are the first four convolutional layers, a simple VGG style stack of layers. The first few convolutional layers generally learns only very basic, small spatial structure, so no point to start a complicated multi-scale computation unit so soon. And we would be much better here with VGG-like starting point, as it has a better reversibility. After this VGG-like opening of the model follows two inception blocks to give the model real multi-scale observation abilities. Overall, we use 4 pooling layers that reduce the spatial resolution from the original 512 or 512 input image to a latent feature map of 32 by 32 by 512 channels. On top of this latent feature map, the model splits to two final paths, one for deciding whether a feature map pixel is somewhere in the middle of opacity or not, and the other to regress the bounding box rectangle around the opacities in case it is. To this branching point, I actually add a third pass, which is an auxiliary reconstruction of the input image. This is kind of an unsupervised alternative for the common and well-known method of transfer learning. I will hopefully talk about it in more detail in some other video. Pay attention that for normalization I use is layer normalization and not the more common batch normalization, as batch norm is not very effective when dealing with very small mini batches, and in this specific case I found it to do more harm than good. In every object detection task, we must make sure that our model has large enough receptive field to cover the largest object of interest. Here it was important to me that the receptive field of the latent feature map will have the potential to cover the full lung area and full spline length. Why this can be important? The most obvious example would be that we do not care for any opacity like mark when it is located outside the lungs. Each and every one of those will be a false positive. Another example is that around the spline there are always something that looks somewhat similar to opacities, but are actually the very normal and healthy pulmonary artery. If we want the model to be able to identify these organs, we must, as a prerequisite, of course, supply it with large enough receptive field to be able to do that. A few minutes calculation gives us accurate numbers regarding the principal receptive field in every layer of our evolving model. Thus, we could easily make changes in the architecture if necessary. In my model here, the receptive field of the final feature map is 182 on 182 pixels. That is if we consider only the dense filters. If we include also dilated convolutions, the receptive field could potentially cover almost the entire image. And for implementing these principles I just mentioned, we must also supply the model with a global context module. In pure convolutional model, any computation unit sees only its fixed receptive field around any pixel and is completely oblivious what's going on in its surroundings. This is highly undesirable, and supplying the model with a global context module is an important way to overcome this limitation. In my implementation, I actually incorporated into the model two different global context modules. To the more common average pyramid pooling, I also added the much less used max pyramid pooling. The latter type of global context machinery gives information about the existence or absence of an attribute in the surrounding of the receptive field. This might be very useful for the specific detection mission. I chose the final input that has been fed to the model to have two channels. The first channel holds the bone-reduced version of the image, and because the bone removal comes with some loss of quality, I loaded the second channel with the original grayscale image. In such a way, I give the model both versions of the image and let it decide by itself what information to take from each one of them. Unlike the regression path of the model, the loss function of the score path needed a more careful attention, as object detection tasks often suffer from extreme imbalance in their classes. As you can see in the ground truth in the left, the gray pixels, which are the positives, are overwhelmed by the number of black negative pixels. For solving this, I chose to use a dice index loss, which is some fine-tuned version based on IOU, intersection over union, thus solving the imbalance problem. However, this raises another problem regarding the proper way to insert images that lack any ground truth bounding box into the training process. This is not a simple issue, as these all negative images tend to pull the trained model into a trivial solution. I solved this by creating a compound image that actually composed of two bottom-top basic images. One is always without any bounding box, and the other always has at least one. Overall, this fully convolutional model had roughly 7 million parameters. The model was trained for 4,000 training steps on a single GPU machine. Small mini batches of 3 compound samples been used as described. Mild dropout of 0.2 was used to assist in preventing overfitting, yet the chain reconstruction part of the model was really the one responsible for successfully preventing overfitting and memorization. Here you can see some examples of the predictions of my trained model. Took the predictions from one session run on 20 images randomly chosen from the test set, and then tried to pick a fair representative 6 of them. This task of pneumonia opacities detection and localization in chest X-ray is actually a pretty hard one. Various reports shows that even when the heavy weapons, the state-of-the-art of deep models, are being taken as the base neural networks, the results are still generally not good enough. You can see some examples for that on the slide. Why is that? The detection of opacities is so out of emission. As I mentioned before, as pneumonia-related opacities do not have any real structured details, many of the advantages of the convolutional model are being lost. To me, it seems that the specific medical imagery task is still waiting for some new kind of a model that will fit more accurately to the specific nature of the problem. A very recent publication from April 2021 claimed to do a significant step towards that, and we'll see what else come in the near future. So that's that for this time. Thank you and goodbye.